Today I'm going to talk about our work Pulsar, which enables ubiquitous and ubiquitous visible light localization. So visible light is known to have the potential for accurate and robust indoor localization, thanks to its deterministic propagation and dense light deployment. In general, there are two types of existing visible light localization systems. The first uses compact and low-power photodiodes and the channel model to derive distances from received intensities of multiple lights. However, this scheme faces practical challenges. The channel model assumes the ideal Lambertian angular response for the lights. However, for practical fixtures, such as tube lights with covers or separators, the assumption is unrealistic. In addition, intensity is vulnerable to partial shadowing and blockage, which is common in practical environments. Together, this can translate into meters of error, which compromises the localization accuracy. The other type of systems uses cameras and photogrammetry to figure out precise locations, which is essentially triangulation with angle of arrival value derived from pixel displacement. But inherently, cameras suffer from narrow field of view, high energy consumption, and long latency combined with their image processing. These limitations prevent camera-based systems from reaching ubiquitous devices and preclude continuous tracking. Given the limitations of existing systems, a natural question arises. Can we design a ubiquitous visible light localization system that is as accurate as cameras, but as energy efficient as photodiodes? As cameras owe their accuracy to millions of pixels deriving the angle of arrival value, we asked the question, can we sense AoA with low-power photodiodes? Here we introduce our solution, Pulsar, which provides ubiquitous and yet accurate visible light localization via photodiode-based angle of arrival sensing. It combines AoA values of 3 or more lights with the location information in a database to compute the precise location of the device. To explain how Pulsar senses AoA with photodiodes, we first need to get back to the channel model, where a single point light source in a dark room is considered. The received light intensity, or RSS, is a product of light's transmitting power, PT, angular response of the light fixture, AT, the propagation loss, alpha, and the angular response of the photodiode, AR. We notice that photodiodes of different designs can have different field of view, thus different angular responses. Since the two photodiodes are co-located, the external channels of these two photodiodes should be identical. This means the transmitting power, angular response of the light, and the propagation loss should all be the same, and thus we can divide these two equations to cancel them out. What's left is essentially the angular response of the photodiodes, which is a function of the angle of arrival. This drops any assumptions about the light fixture. What we get is essentially a ratio of the RSS from the two photodiodes equaling to the function of the angle of arrival. Note that this function is fixed once the photodiodes are manufactured, so it can be measured and calibrated in advance. Inverting the equation, we can get a function that maps RSS ratio to angle of arrival, which basically implies that we can now use a pair of photodiodes to sense the AoA. Note that the channel model can be applied to each intensity modulation frequency separately. Thus, the AoA can be computed for every intensity modulation frequency, since the RSS value can be computed for each frequency. Once we know the AoA value of 3 or more lights, we can triangulate the sensor's 3D location. But first of all, the lights need to be separable from each other. We have observed that existing fluorescent and LED lights exhibit natural and unique flickering frequencies, which can be used to identify each light. The frequency is thus called characteristic frequency. As a result, we can separate the lights in frequency domain. Intuitively, this should be as easy as extracting all the peaks from the frequency domain, assuming noise floor is clipped at some fixed RSS level. However, that wasn't actually the case. In reality, what we get is a whole bunch of frequency peaks in the spectrum, those whose numbers greatly exceed the number of lights observed. If we zoom in on the frequency components of a single light, the problem becomes clear. We can see that the terms of spurious artifacts around the strongest characteristic frequency, which can easily mask away faraway lights that have lower RSS. These spurious peaks can come from lights themselves due to power line harmonics being modulated on the characteristic frequency. However, they can also come from motion artifacts and dynamics in the channel, such as vibration. Luckily, we observed that all these kind of processes does not affect the AoA value significantly. Thus, the frequency coming from the same light should have the same AoA value, and frequency components with the same AoA value are likely originated from the same light. As a result, for each AoA cluster, we can just pick the strongest frequency components as a characteristic frequency. Essentially, we can separate the lights in the angle of arrival space, then extract the characteristic frequency from the artifacts among the same AoA cluster as it has the highest RSS value. Finally, we need to identify each light in order to obtain their location for triangulation. However, it is known that matching each individual light to their identity will result in poor accuracy due to frequency drift. We observe that if we match individual lights, the correct match is within the few ones of the least frequency error. Meanwhile, lights sampled together should be physically close to each other. So, Pulsar identifies lights as a group. For each frequency, it chooses 2 to 3 possible identities from the database with least frequency error. Then, by combining different possible identities of different lights, groups of candidates can be formed. After that, Pulsar scores each possible group based on both physical distances and frequency error as given by the database. Finally, the group with the best overall quality is selected as the correct matches. The actual localization process is very simple. With unknown user coordinates, light coordinates from the database and 3 AoA value, we can form 3 unique vector equations. Then using numeric solver, we can derive the user's location. If a false light is visible, we can even compute the phone's orientation on the horizontal plane. Finally, Pulsar also addresses the light registration process, where each light's location and frequency have to be collected and entered into the database. During the process, the location of each light will need to be measured and entered manually. We know that even smart bulbs do not solve this problem since they do not know their own location automatically. So their identities and locations still need to be manually associated. To reduce the burden of light registration, we utilize Google's Project Tango to gather a series of relative motion tracks. We then scale the traces to fit the map and derive the physical location of each light, thus eliminating the need for measuring the location of each individual light. We implemented the Pulsar sensor as a USB dongle, which can be fitted to existing smartphones, and the Pulsar software as an end-to-end Android application. In addition, Pulsar can readily augment future smartphones, robots, and wearables, as it only requires 2 compact photodiodes. We first evaluate performance of the angle of arrival sensing scheme. We place the prototype Pulsar sensor at different distances from different types of lights and measure the angle of arrival airon with a motorized platform. With a fluorescent light bulb, 90th percentile AoA airon is 8 degrees, even at a close distance of 1 meter, where the bulb should appear quite large instead of point source. With even larger tube lights, the accuracy does degrade notably, but it is still within 12 degrees. We then evaluate the accuracy of light identification. In practical environments, Pulsar's identification accuracy is over 90% with just a single measurement. This enables Pulsar to provide instantaneous location fix without any user intervention. And in theory, if we operate Pulsar with smart LEDs that have randomly allocated frequencies but less frequency drift, the accuracy can reach close to 100%. Our experience shows Pulsar's 90th percentile localization accuracy can reach 10 centimeters. However, the accuracy decreases with increasing ceiling height, as the same angle of arrival airon can translate into more displacement. But still, the accuracy is 4 times better than previous RSS-based systems. We also noticed that Pulsar can provide orientation information with high accuracy, as long as the sensor surface does not parallel the ceiling. Pulsar's total latency is under 1 second, which is at least 50% faster than previous camera-based systems. Nearly 2/3 of the latency is consumed by USB transport, FFT calculation, and peak finding, which can be improved significantly by new hardware design and algorithms. The rest 1/3 are mostly sampling. Identification and location solving consumes negligible time. Pulsar also have 63% lower power consumption than previous camera-based systems end-to-end, and uses 82% less energy per location since it reports location twice as fast. The sensor dongle itself consumes around 150 milliwatts, but with the latest out-of-the-shelf components, the total power consumption can be cut down to 10 to 20 milliwatts without other modification. These results show that Pulsar's novel design has enabled reliable and accurate visible light localization with reduced latency and low power consumption, well suited for the ubiquitous applications. That concludes my talk, and if you are interested in my paper, please visit the website shown on the slides. Thanks for listening, and I will be glad to take your questions.